section 7.6, the last section of chapter 7, except for review. So once you get through this one, you've made it. Toughest chapter in the course will be over. Okay, so what we're going to look at is the derivatives of the inverse trigonometric functions. And we're actually going to look at three of them. We're going to look at the primary trigonometric functions, sine, cosine, tan, in fact the inverse of those. So we won't look at secant and cotan. Of course there are derivatives for those as well, but it's somewhat similar to this, so we'll keep it a little bit easier for this year. This is all your book does, and then next year you can also take into account cosecant and secant and cotan. But if you get this, you'll understand the other ones as well. Alright, so here we go. Here are the derivatives. I'm not going to read them all out here, but just for example, the derivative of the inverse sine of x is equal to 1 over the square root of 1 minus x squared. Okay, so let's start by proving the first one, showing that it's true. And in order to prove it, what we're going to have to do is to take into account that y equals inverse sine of x is exactly the same as what? Well, saying that the inverse sine of some amount is y is the same as saying that x is equal to sine of some angle y, right? These two things are exactly the same as each other. We've talked about this a few times recently. So with that in mind, what we can do is use implicit differentiation of this, of x equals sine y. So we're going to find d dx of this side, x, take the derivative of x, and we're also going to take d dx, so that's the derivative in terms of x, of sine y. Okay, so implicit differentiation. If it's just an x, you just do it normally. If there's a y, though, you have to put that y prime after. So derivative of x is just 1. The derivative of sine y. Well, we start with the outside function, which is sine, and the derivative of sine is cosine, so you get cosine y. But this is a y here, so now you have to take the derivative of the inner function, which is y, and you get 1 y prime. And what we do is we solve for the y, so you end up with y prime equals 1 over cosine y. Now that does not look like this, so what's going on here? So what we're going to do now is we're going to use an identity. We're going to use the Pythagorean identity, sine squared x plus cosine squared x equals 1, but we're actually going to write it, since we're using y's here, we're going to actually write it with y's. We're going to put sine squared y plus cosine squared y equals 1, and we want to isolate cosine y. We want to get cosine y by itself. So we'll have cosine squared y equals 1 minus sine squared y. Just move this over to the other side. Then because it's cosine squared, I don't know what that was, cosine squared, we have to take the square root of both sides, so you get cosine y equals the square root of 1 minus sine squared y. So that's what we can write in the denominator now. Y prime equals 1 over the square root of 1 minus sine squared y. But look back up here. We said that x is equal to sine y. So if we have sine squared here, it's just the same as x squared. So we have y prime equals 1 over the square root of 1 minus, instead of sine squared, x squared. And that's exactly what we were trying to prove here. We've done it. Okay, let's take some derivatives. Inverse sine of 1 minus x squared, we want to take the derivative, so we want to get y prime. So we look back up here and we see that the derivative of inverse sine is 1 over, so 1 over the square root of 1 minus x squared. But remember, that x and that x are the same, or in the one we're doing right now, this 1 minus x squared is going to fit in right there. So you're going to have 1 minus x squared, and then it's squared, so squared. Okay, that's the outer function, the inverse sine. But we also have an inner function, which is this circled bit here. So we're going to use the chain rule. We're going to multiply by the derivative of 1 minus x squared. And the derivative of that is negative 2x. So it's time to start simplifying. We get 1 times negative 2x is negative 2x over the square root of 1 minus. Now, we got to square 1 minus x squared. So that'd be 1 times 1 is 1. 1 minus x squared is negative x squared, and then negative x squared times 1 is another negative x squared. So you get negative 2x squared. And then negative x squared times negative x squared is plus x to the 4th. So we'll keep the numerator, the negative 2x, all over square root 1 minus 1. Nothing, gone. Take away negative 2x squared. That makes positive 2x squared. Take away positive x4 is negative x to the fourth. See what you can do next? You can factor out an x squared on the bottom. So you end up with negative 2x all over the square root of x squared. We factor that out, and what we still have is 2 minus x squared. Now, why do we do this on the bottom? Because you now have something, this x squared, you can actually take the square root of. Do you remember what the square root of x squared is? You're going to hate this. Ready? The square root of x squared is x. Absolute value. Do you remember that? If you have an even exponent, 2, and then you take the square root and you get an odd exponent, 1, you have to slap absolute value signs on it. I'm not going to explain why because it takes a long time to explain, but you should actually know that, and I'll explain it in class if you forget. Then keep the 2 minus x squared. So that's a great answer right there. There is another way you could express this answer. So I'll say or. Okay, there's 3 possibilities here. One possibility is that x is equal to 0. And actually, that's not even a possibility, because if x was equal to 0, then your denominator would be 0. You'd have 0 times something, which equals 0, not allowed. So there's actually 2 possibilities. Either x is greater than 0, or x is less than 0. So let's consider both of those. Let's say, first of all, that x is greater than 0. If x is greater than 0, these absolute value signs actually don't do anything, so you could just kind of ignore them. And this would still be positive, because x is greater than 0. So you'd have x over x, which cancel out. All you'd have left is negative 2 over the square root of 2 minus x squared. That's if x is greater than 0. Now, what if x is less than 0? Well, if x is less than 0, these absolute value signs would make it positive. But this here would be negative, right? X is less than 0 means negative. So you'd have a negative times a negative, which equals a positive. So instead of having negative 2 on top, you'd have positive 2 on top. The x's would still cancel, and you'd be left with the same thing on the bottom, square root of 2 minus x squared. That's if x is less than 0. So another way you could write this, you could either write it like this, y prime equals all this, or you could say y prime equals all of this. This is piecewise notation, as we learned about in grade 11. Many of you despised piecewise notation, but it is good if you understand both these ways of expressing the answer. Okay, way back up here. Y equals x times the inverse tan of square root of x. This is going to be the product rule here. So we're going to do y prime equals, the first piece is just this x. So we're going to take the derivative of x, which is 1, and multiply it by the second part, which is inverse tan of square root of x. So square root of x is 1, and multiply it by the second part, inverse tan of root x, plus the first part, which is x, times the derivative of the second part. So we got to take the derivative of inverse tan of something. Well, it says right here for inverse tan, it's equal to 1 over 1 plus x squared. But in this case, your x is this root x. So it's going to be root x squared. Then you have to multiply, using the chain rule, you have to multiply by the inner function, this root x. So that's x to the 1/2, remember. Some of you have memorized this. I'll just write it over here. X to the 1/2. And you know the way you take the derivative of this is you move the 1/2 down, x, and then the 1/2 becomes negative 1/2. So I'll write that right here, times 1/2 x to the negative 1/2. Okay, let's see how much we can simplify here. I don't think there's anything we can do with the first term except leave off the 1. So inverse tan of root x. Now, what do we have on the top here? We have an x, 1, and 1. So just x. So we have plus x all over 1 plus root x squared. Well, that equals x. And then we're multiplying that by this. We have a 2, and we also have this x to the negative 1/2. Well, that's a flippin' negative. It comes to the bottom, and 1/2 means square root of x. Okay, I think this will be our last step. Keep that first term the same. Now, let's look at our x's. You have 1x up here, and you have 1/2 down there. So the rule when you have the same base and you're dividing is to subtract. 1 minus 1/2 is 1/2. So you end up with 1/2 on the top. I think I've just given myself one extra step. And on the bottom, this is gone now, right? We already got rid of this. So what we have on the bottom is 1 plus x2 or 2, 1 plus x. In fact, I'm going to make it x plus 1. What the heck? Same thing. And finally, I guess, just to complete this, I don't want to write this as x to the 1/2. I want to write that as square root of x over 2 times x plus 1. This is a great answer. If y equals inverse tan of x over y, find dy dx. Can't isolate that y. You're going to have to use implicit differentiation again. Okay, I've written the derivative over here to help us out, and what we want to know is the derivative of both sides in terms of x. So first of all, the derivative of y is 1, but there's a y there, so it's 1 y prime, or just y prime, equals inverse tan, here it is right here, it's equal to 1 over 1 plus x squared. But in this case, your x squared is x over y all squared times, now when you times, you're going to have to take the derivative of this piece here. And this, you're going to have to use the quotient rule. So for the quotient rule, take the derivative of the top, which is 1, multiplied by the bottom, which is y, minus the top, which is x, times the derivative of the bottom, which is 1 y prime, and you divide all that by the bottom squared. Okay, let's do some simplifying. We have y prime equals, well, on the top, we're just going to have this y minus xy prime. And on the bottom, we've got 1 plus, let's expand this, so we've got x squared over y squared. And you're multiplying that by y squared. So if we keep going here, we'll keep the top the same, y minus xy prime. On the bottom, it works out nicely. You have 1 times y squared, which is y squared, and you have x squared over y squared times y squared. Well, the y squareds cancel in that case. You just get x squared. So now what we eventually want to do is we want to get the y primes by themselves. So I think what we should do is get rid of this denominator here. So multiply both sides by y squared plus x squared. So over on this side, you'll have y squared plus x squared, or x squared plus y squared. It's exactly the same thing, multiplied by that y prime, and that'll equal y minus xy prime. Okay, let's move this term, this xy prime, over to the other side, so we have both the y primes on the same side. So I'm going to move up here. I'm going to have x squared plus y squared y prime, that's what I already had on this side. Then I'm going to move this over, so it's going to be plus xy prime equals y. Now I have y primes in both these terms. I can factor out a y prime, and what I'm left with when I do that is x squared plus y squared plus this x right here equals y. Last thing I have to do is divide both sides by this square bracketed piece. So I get y prime equals y over, now I don't need all these brackets, I can just write x squared plus y squared plus x, and that's our answer. Okay, here's the derivative we're going to need in this question. Differentiate y equals inverse cos sine x and use the result to sketch the graph. So here's our argument. This is one of these weird ones where you have a trigonometric ratio with a trigonometric ratio as an argument. But we just follow the same rules as before. So the outer function here, we're going to find y prime, and our outer function is inverse cos. And this is our derivative right here. For inverse cos, when we take the derivative, you're going to have negative 1 over the square root of 1 minus x squared. But in this case, x is sine x. So it's going to be 1 minus sine x squared, or sine squared x. Same thing, right? Now you have to take the derivative of the inner function, this circled part. So the derivative of sine x is cosine x. So what we have is negative 1 times cos x is negative cosine x over the square root of, now look at this, 1 minus sine squared x. What does this make you think of? Makes me think of this again, sine squared x plus cosine squared x equals 1. Or if I take this sine squared x and move it over, I'll have cosine squared x equals 1 minus sine squared x. So where it says 1 minus sine squared x here, I can put cosine squared x. Good. On the top, we have negative cosine x. On the bottom, the square root of cosine squared x. What's the square root of a squared thing? It's just cosine x. But hey, wait a minute, we went from an exponent of 2 to an exponent of 1, which means absolute values on this. So this is a good answer. Let's see if we can answer it that other way like we did down here. Let's try to do this as well. So again, there's three possibilities. Either cos x equals 0, which isn't possible because you'd be dividing by 0, or cosine x is greater than 0, or cosine x is less than 0. So let's say it was greater than 0. If it was greater than 0, the absolute value signs would do nothing. You'd have positive cosine x on the bottom, you'd have negative cosine x on the top, and they could just cancel each other, the cosine x and the cosine x. You'd end up with negative 1. So negative 1 if cosine x is greater than 0. What if it was less than 0? Well, if it was less than 0, this would still be positive because it's an absolute value signs. But this would become positive as well because you'd have negative times a negative, which is a positive. So there'd be no more negatives. You could cancel out the cosines. You'd be left with 1 if cosine x is less than 0. So y prime equals all this, or you could say y prime equals that. Now, if you look, I didn't actually say this, we want to sketch the graph of this. So I'm going to set up the graph. So it doesn't say the domain, but I'll go from negative 2 pi to 2 pi. Let's find the y-intercept first by putting 0 into this. If you put 0 into this, you get sine 0, which is 0, and then inverse cosine of 0. When is it that cosine equals 0? Pi over 2. You could say 3 pi over 2 as well, but remember, when we do inverse cos, we're restricting the domain to the first and second quadrants. So pi over 2. So our y-intercept is pi over 2. I'll put our point right here. Now, pi over 2 is 90. In between 0 and 90, cosine is positive. And actually, even between negative pi over 2 and 0, it's also positive, right? That's the fourth quadrant. And cosine is positive in the fourth quadrant. It says here, if cosine is positive, the derivative, or the slope, is negative 1. So from here to here, we just want to draw a slope of negative 1, which is like a 45-degree angle. Now, we could check this if you want, but I'm asserting that probably pi over 2, if we put pi over 2 into our x, we're going to get 0 as the answer. Let's see, sine pi over 2. Well, sine pi over 2 is 1. When is it that cosine equals 1? Inverse cos equals 1 when it's 0 degrees, so that absolutely worked. Okay, from pi over 2, which is 90, all the way up to pi, cosine is negative because that's the second quadrant. And from pi to 3 over 2, that's the third quadrant, it's also negative. So it's negative both of these regions here. When it's negative, that's down here, the slope should be 1. So now it should be at a 45-degree angle up this way. So I guess it should end up back at pi for 3 pi over 2. Do you want to try that? Well, what the heck. 3 pi over 2, if we put it in here, sine of 3 pi over 2 is negative 1. When does cosine equal negative 1? When it's pi, and that's how high it is. It's up at pi. Its y value is pi. So you can probably see the trend here. You're going to go over 2 quadrants effectively, negative 1, up 2 quadrants, positive 1, down a couple quadrants, negative 1. Same with over here. You'd go down 2 quadrants down to here at negative 1, then up 2 quadrants again at positive 1. And this is basically what your graph looked like. Why did I stop here? Because actually it would go beyond 2 pi before it reaches the x-axis again. This would be at pi over 2 right there. Okay, if this doesn't make sense, try some of these points into the original function and you'll see that you're getting exactly the values that I've suggested here. But this was very helpful in order to draw this graph. Much more helpful, for example, than this one up here. I can't stand this indecision.